Hello, my name is Vitor DosAnjos. I'm from Swarthmore College. I'm going to be presenting work that me and my colleagues are currently conducting in order to estimate the population size of the North Atlantic right whale. Given the audience, I'm not going to spend too much time going over this, but I will say for the uninitiated that the North Atlantic right whale is the most endangered large whale species in the world, and that there have been extensive conservation efforts to prevent the species extinction. Getting an accurate estimation of the population size could have important implications for these conservation efforts and for the future of the species as a whole. So I will also say that we are not the first group to try and estimate their population. This has been done various times by various teams throughout the decades using different methods. What we hope to do is use different methods which make different assumptions and try to add to the conversation via that method. One such difference in our methodology is that we did not use a capture mark recapture framework. I'll also say before I get into the presentation that this is toy data. We are not presenting our actual results yet. Next year, we will be presenting our actual results. I'm here to present on our methodology and get feedback from the community so that we can come back next year with the best results possible. So I would also like to thank the North Atlantic Right Whale Consortium for letting us use their sighting database as of February 2020. The date and time, so we have 70,403 whale sightings from the database, and each sighting has covariate data recorded for each individual. Some covariates are sex and being entangled, for example. Some statistical hurdles inherent in estimating population size is using sighting data alone is that one, it's unlikely that all alive individuals will be seen throughout the sampling period. Two, we cannot be certain of the living status of an individual unless we have seen that individual dead. Three, the likelihood of a whale being seen is not consistent in time or space. And four, the likelihood of a whale being alive is not consistent based on various variables that significantly influence its survival. This is the outline that we'll be using to order our discussion of the methodology. So the first part of the discussion will be how we estimate probability of alive given sighting and covariate data. The second part of our discussion will be how we estimate the number of individuals that are alive but have never been seen, number of individuals that are alive but have never been seen. And then the final part of our discussion will be how we use the distribution of, so how we repeat steps 1 and 2 1,000 times and use that distribution as a range of possible estimated population sizes. So a range of possible current population sizes. So to begin with, I'm going to use this table to heuristically go over what we do. This is, again, toy data for illustrative purposes, but this is somewhat similar to what our data actually looks like, what our table actually looks like when we're doing our analyses. So the first column is a whale ID, which is unique to every whale that has been seen and not confirmed dead. So every row in our table are whales that have been seen, not confirmed dead, and yeah. Next column is sightings. So these are the years in which that individual was sighted across a sampling period. The next column is our estimated probability of being alive given only sighting data. So notice that in row 1, the probability of being alive is high because that individual was sighted recently and somewhat frequently. Compare that to row 2, where the probability of that individual being alive is very low by our sighting data because that individual was seen less frequently and a lot more in the past. The next column is our incorporation of covariate data to adjust that probability of being alive given sightings, either up or down. And finally, this column represents our first sample, and the last column represents our last sample. In our real table, we have 1,000 columns instead of just these two. And we use these columns as to create the distribution. How we get each column, right? So for every row, imagine there's a coin, and that coin is weighted to land on alive, proportional to the previous column. So for the first row, that coin is weighted very heavily to land on alive. And in the second row, you see that that coin is weighted very heavily to not land on alive. So what we do for each sample and every whale is that we flip each whale's unique coin. And if it lands on alive, we say that whale is alive for that sample. If it lands on dead, then we say that whale is dead for that sample. We do that for every whale. We then repeat this 1,000 times to get our 1,000 samples. And what we do in the end is that we sum up all of the alive individuals for each sample. And these are 1,000 possible estimates of the population size given the sighting data. This is not complete because it does not incorporate the number of whales that are alive, an estimate for the number of whales that are alive that have never been seen, which will be the second part of our discussion. So there are three possible ways to estimate probability of alive using sighting data, each using different assumptions. So the first kind of method assumes that there is equal probability of being alive, there is equal probability of sightings occurring throughout the sampling period and regardless of the population size. These assumptions are obviously unrealistic. However, we use them as a sanity check. So we use a method here. So we use a method, specifically Solo 1993, that makes these assumptions, and this is a sanity check. We also use a second method, which we believe to be better, and that's called the adjusted beta method, which I will discuss soon. The second kind of model assumes that there is not an equal probability of sightings occurring across time, but necessitates that you independently estimate sampling effort. We believe this to not be ideal because it's very difficult to unbiasedly estimate sampling effort. So the third kind of model, which we believe to be the best, does not assume there is equal likelihood of sightings occurring throughout time and does not require an independent estimation of sampling effort. The way that these models generally work is that they use the sighting data itself to estimate sampling effort. The specific implementation we use, like I said recently, is the adjusted beta method described in Wang et al. 2017. We believe this to be the best model, making the most realistic assumptions given the data. And this is what we use in our final results. So finally, we incorporate covariate data into the adjusted probability of being alive using a maximum likelihood approach. Specifically, what we do is that we fit various variables, covariate variables that we believe to significantly impact likelihood of survival for individuals. We use all 70,000 sightings from the sighting database, and we try and estimate the effects of each variable on likelihood of survival using logistic regression. What we do specifically is that from that logistic regression, we get the coefficients of those variables, and then we use those to either increase or decrease the probability of alive from the sighting, estimated probability of alive given sightings. The next part of analysis, I will say, so before I show graphically what this looks like, I just want to go over what we know and what we don't know. What we know is the number of individuals that we have seen once, the number of individuals that we have seen twice, the number of individuals we have seen three times, all the way to the individual we've seen the most times. We know what that distribution of like alive individuals and how many times they've been seen. We know what that distribution looks like. What we do not know is the number of individuals that are alive when sighting equals 0. So individuals that are alive that have never been seen. One strategy of estimating the number where sighting equals 0, so number of individuals alive that have never been seen, is to plot all of the alive individuals and find a regression that fits that data best, and then use that regression, specifically the y-intercept from that regression, as the estimate of the number of individuals that are alive but have never been seen. So what this looks like. So this is what it looks like. So for every sample, again, I should say this is at the sample level. So for every sample, all of the individuals that are alive, we plot on the x, the number of times, so on the x is sightings, on the y is number of individuals seen that many times. And what we do for every sample is we plot the number of individuals alive. And then what the green here represents is the regression that fits this data best. So circled here is a blue dot. That blue dot is the y-intercept of the regression one. And what that means is that's the estimated number of individuals that are alive but have never been seen according to this regression. Finally, the third and final part of our analysis is incorporating steps 1 and 2, repeating steps 1 and 2 1,000 times, and then using that distribution as the estimate of possible population sizes. So graphically representing our outline, this is what it looks like. So for every sample, using the individuals alive for that sample, we estimate the whales that are alive but have never been seen using the method described in step 2. Highlighted in red here is the estimated number of individuals alive for that sample using the sighting data. So when you combine these two, you get a single data point, and what that single data point represents is one possible estimate given our methods of the population size. When you sum all of the 1,000 points together into a histogram, this represents a distribution of possible population sizes given our data. So if you have any feedback, please please reach out to us in this email, especially model-specific feedback. And I'd also like to thank these people for making this research possible.